quadratic functions can be used to solve or model several different real-life problems. So we can solve problems like finding maximum areas, or we can simulate the flight path of a ball, and we can use the key features here, the X-intercepts, the Y-intercepts, and the turning point, to give some context to the problem. For example, if I threw the pen that I'm using out the window, right, here's the window here, and I threw it out, it might have a flight path like that. So I throw it out, it hits its turning point here and lands down here, which is the X-intercept, and it was thrown out the window that had an initial height of 2 meters high or something like that. So the key features, X-intercepts, Y-intercepts, and turning point, all have some context, so must be interpreted in context. When we're modeling real life situations, make sure that the graph actually matches up with the context of the question. For example, if a ball's being kicked off the ground, your parabola should not look like that. Okay, no one kicks the ball at this height here, down and then back up again. Okay, so make sure that you understand what the graph is should look like to model the scenario. All right, so let's go for it on this question here. So we're going to maximize the area of a rectangle. So a piece of wire measuring 100 centimeters in length is bent into a rectangle. Draw and label a diagram to represent the rectangle where X is the width, and let's just say that Y is the length. All right, use the perimeter to write an expression for the length of the rectangle in terms of X. So the perimeter is going to be 2X plus 2Y equals 100. How do I know it was 100? They told me that the wire length is 100 in total. All right, so now they want the perimeter in terms of X. So that means make Y the subject, okay, and have it in terms of X. So that's 2Y equals 100, take 2X. Y is equal to, I'm going to halve both of these amounts here, 50 take away X. All right, write an equation for the area of the rectangle in terms of X. So area equals length times width. Now we've just got X times Y here. Now that's really difficult to solve when I've got two variables here. But note that down here we found Y in terms of X here. So Y is equal to 50 take X. So instead of using X times Y, what I'm going to do is go area equals X multiplied by, and not Y, I'm going to say that Y is 50 take X. And notice, girls, that this is just a parabola. So decide on the suitable values of X, restricted domain and quadrants. All right, well, let's have a look at the graph first of all and see if we can work out what the values of X could be. 50 take X. Right, now a quick look at this and you can see that the X-intercepts are going to be X is equal to 0 and X is equal to 50. Right, so the domain on my calculator goes from -7 to 7. So I need to increase it massively. So I'm going to hit this 4 arrow button here and send it all the way out to around about 60. The maximum value is 4.6 at the moment. That's going to have to get a lot bigger. Okay, so I'm thinking like 100 for argument's sake. All right, now we check it and graph it, and not much happened, did it? There it is. Okay, so you can see that the turning point is way up there. All right, so we can increase that significantly. Let's send it up to 700. Try that. Oh, we got it. Okay, so when's it going to be true? Well, the first thing I think is we should sketch the graph of it first. And sorry about the formatting here. It's correct on our Word document, but it's just not coming out correctly in the PDF document. But let's sketch this thing. So we've got our Cartesian plane that we're going to put together. And what we're going to note is it's got an X-intercept at 50 and another X-intercept at 0. That means that the axis of symmetry is going to be on the line X is equal to 25. And where's the turning point going to be? Well, what I could do, girls, is because this is a calculator question because it's modelling, I'm going to substitute 25 in for x. All right, so that's going to be 25 multiplied by 50 take away 25, which is 625. Now, note the domain. So what I'm going to do here is, and I'll explain in a sec, I'm going to put a point in for the turning point. I'm going to put an open circle here and an open circle here and draw my parabola like so. Okay, now why doesn't the parabola continue on? Well, these are values for x and these are values for area. Okay, now x can't be a negative side length. Okay, so you can't produce a value of x that's negative, okay, because it's a side length. Okay, again, think about a rectangle with a side length of negative 3 meters. Doesn't exist. Okay, now the other thing is that x has to be less than 50 because 50 take away x, if x is more than 50, that will become negative. Okay, so x has to be a value between 0 and 50, and it can't be inclusive of those values themselves because the reason for that is that I'd be trying or attempting to make a rectangle with a side length that is 0. Okay, and that doesn't exist either. Okay, so that's our function there. Now let's label our key features, which is 50, 0, 0, 0, which is at the origin, 25, 625, and we've got everything we need. So decide on the suitable values of x. What we're going to do is say that we've got 0 less than x less than 50 as the domain. They're the suitable values for x. Use the graph to determine the maximum area that can be found. So these are all the different areas depending on the value of x chosen. But this is the largest value for area. It's 625. So we're going to say that max area is 625, what is it, centimeters, meters? Centimeters squared. What will be the dimensions of the rectangle to achieve it? So remember what we've got is x times y, or length times width, which is going to be 50 multiplied by, it's going to be 25 multiplied by 50, take 25. So the length is 25 and the width is 25, and we've got to put a unit in, centimeters and centimeters. So it's a square. Okay, so one thing to note there is that you can maximize it by a square. All right, just a couple of things to note on the calculator. So let's go back to graph and table and graph it. All right, we can go analysis, G-solve, and we can get the maximum value by hitting this max button here. And that'll show you what the turning point is. So it's pretty handy. We can get the X-intercepts quite easily by going analysis, G-solve, and root. All right, root, and then you use the arrow key to move left or right between the roots, okay, or the X-intercepts. Right, flight path of a ball. Now we've got a soft foam ball is thrown upwards from the top of a 120-meter building. The position of the ball above the ground, h in meters after a certain time t, is given by this particular function here. Right, so what I'm imagining is some sort of scallywag kid is up on the top of a building, got a ball, soft foam ball, throws the ball from the top of the building or rolls the ball off. No, it's thrown upward. Okay, so it goes like that and then falls. All right, what's the initial height of the ball? That occurs when t is equal to 0. So when time is equal to 0, we get the initial height. That's going to be negative 10 squared, which is 100. 100 multiplied by 1/10 is 10. That gets negated, negative 10 plus that. So when t is equal to 0, h is equal to 120. And that is going to be meters. Now, of course, that makes sense with the context of the question because the ball is thrown from the top of the building, which is 120 meters off the ground. how long was the ball in the air? So what we're going to do is consider the graph of this. So it gets thrown off at a height of 120, goes up and comes down. And where it hits the ground is the length of time the ball is in the air. So I'm going to get the X-intercept. All right. Now there's a couple of ways to do this. So I'm going to show you graphically how to do it, and I'm going to show you with the main screen how to do it. Let's pop our new function in, -1 on 10 multiplied by x take 10. Now note you need to use x's and y's in this screen, not h's and t's, 130. All right, so let's think about our domain. Ball starts at a height of 120. So what's our top y value going to be? Maybe it goes up to 140, 20 meters higher than it starts. I'm not sure. How long will it be in the air for? Now, currently, the X maximum value is 60. That's a long time to be in the air. I reckon 20 seconds maybe. So we'll go, okay, and let's just see if we can get the graph. Whoa, it's in the air way longer than that. All right, so you can see here I've gone at a length of 20 seconds, but it seems to be way longer than that. It's coming down, but yeah, not far enough. So let's just change this to, I don't know, 120. Yeah, we got it. Okay, so this value here will give it to us. So we can go to analysis, gsolve, and root. And there we can see it. It's 46.95. All right, so that's one way of doing it, is with the graph and tab. All right, but that's not my preferred method. Okay, so what we're going to do is go into the main screen, and I'll show you how we're going to do this. What we're going to do is grab the solve function. And we're going to say that I've got this function, 1 over 10 multiplied by x take 10 all squared plus 130. And I want to find out when it's equal to 0. Okay, that is, I want to get the x-intercepts. I want to solve for x. All right. And interestingly, it's told us that we've got two x-intercepts here, one at -26.05 and one at 46. Now, it's our job to know that one of those x-intercepts, which would be this one here, is irrelevant. Okay, that's not where the ball starts. The ball didn't start back here. It started or was thrown from 120 high. That was the initial value. So we can ignore this value here, okay, and we can only take this. The other thing to note is it doesn't suggest how many decimal places to round it to. So what we've got to do is actually go into standard form and repose the question, because the actual answer is this exact value here. So how long was the ball in the air? It would be from 0 seconds all the way to 10 root 13 plus 10 seconds, which is approximately 43 or 44, whatever it was, I can't remember. Right, so that's how long the ball was exactly in the air. Now, how did I know to use an exact value there? It's because there was no suggestion on the number of decimal places to round to. What is the appropriate domain or t-values for the path of the ball? So we're going to say that it is from time 0, less than and equal to, because we can include that endpoint, okay, because at time 0, the ball is like in the person's hand, all the way up to 10 root 13 plus 10. All right, so they're the acceptable values between there and there. Now the ball doesn't continue because it doesn't obviously burrow into the ground or get wedged down and drill itself into the surface of the core of the earth, okay? So it stops when it hits the ground. In fact, in truth, what it will probably do is bounce until it becomes stationary, but we'll pretend that that didn't happen. What is the maximum height that the ball reaches, and how long does it take to reach this height? All right, so for this one, we're absolutely going to go back into graph and table, regraph the function, and ask analysis, gsolve, and max. We're going to get it to tell us the maximum value. So the maximum height is 130. Gee, I could have found that straight off the function as well, because that's in turning point form already, and it's going to be at 10. So kind of like a good example of why you should look at the function rather than the graph itself. But anyway, the maximum height is 130 meters, max height. at time t equals 10 seconds. Right, sketch the graph, no worries. No, that's not 130. That value there is 10 root 13 plus 10. This value here is 120. All right, that's about 48 or 50. So 10 will be around about there. And we'll go 20, 40, 60, 80, 100. There's 140. So it's midway there. So the ball goes up and then down. Endpoint, endpoint, turning point. 10, 130. 0, 120. 10 root 13 plus 10. Fully labelled axes where t is equal to time and h is equal to height. How long will it take the ball to be 40 metres above the ground? Right, so you can see here that what we're after is this point, 40. All right, so there's two ways again we can do this, but I'll show you my preferred method first. So we're going to go to main again, and this solve here solves when the y value is equal to 0, i.e. the x-intercepts. But we can actually ask the question, when is the y value equal to 40? Okay, and it's going to tell us the answer to this. So let's just see what it says. So it's when x is equal to negative 20 and x is equal to 40. Now notice that the negative solution is because the parabola goes down like this and the calculator doesn't know that this is a soft foam ball. Okay, so we're going to say that it takes, how long is it? It's going to be when x is equal to 40. So when t is equal to 40 seconds, the ball will be 40 metres above ground. Okay, we're not going to include that negative one there because that's saying at negative 20 seconds, i.e. 20 seconds before the ball was thrown. It was, and it wasn't. The ball's stationary there at this point in time and was thrown. So these values of t are not appropriate. How high above the ground is the ball after travelling for 30 seconds? All right, so this was about 50 seconds, so 30 seconds would be somewhere there. So what we would do to find this out is we would grab this function here, which is the ball function, and pick it up and drop it there. And what I like to do is use this key. It's in keyboard and it's in math 3. It's the with key. And we're going to say with a value of x of 40, i.e. substitute x is equal to 30 in, and that'll tell us the height at that point in time. So it's 90. So when t is equal to 30, height is 90 metres above ground. All right, how would I do that in the graph screen? Again, I'd prefer to use this method here because if the values are irrational numbers, then exact solutions will be produced by the main screen. But this version here will always give you approximations. But we can do it anyway for this one because it does produce rational answers. Right, so how long will it take to be 40 metres above the ground? So G-solve. All right, what I want is the length of time. That's an X calculation. And what that says is, tell me, I'm going to give you the X value when Y is equal to what? So 40 metres above the ground. So we type in 40 there. And what it does is it produces the 40-40 that we found before. Note that if I move the arrows around, no, it's only going to give us the positive one because the negative one is out of the screen. So that's how I could have done it, is by using G-solve. And the same thing for this one. How high above the ground is the ball after travelling for 30 seconds? I could use analysis and G-solve on that one. And I'm going to do a Y calculation this time. And it says, give me a value for X. So let's give it a time of 30 and ask it to go find it. So 30, 90. When t is equal to 30, the height is equal to 90. Right, so again, notice that this is good when it gives rational answers, but if it's irrational, it will always give you a decimal approximation. And we saw from this particular question here that we want the exact value when there's no suggested rounding. All right, so your exercise now is 7F. We'll supplement this particular set of work with some more questions or some more analysis problems. So stand by from them or for them in the second half of the double period.